this was the demo. Okay, I've told you about this. I've told you about the evo loop. If you're interested in it, go to this URL, then you'll find all the information about it. It is a self-replicating structure with DNA inside the loop. DNA is copies, we had this already. Yeah, we had this already, but I want to come back to the theme artificial life in cellular automata. Because what generally is interesting about it is that everything about the loops that we've seen and all the other rules, it's, as I said before, it's the result of only local rules, because it only looks at local rules. You could parallelize this calculation, for example, very easily, because you don't need global information to calculate the next state of each cell. And it shows evolution without such things as a concept of individuals. So normally, when you do genetic algorithms, you have something like, you have an object that represents individuals, and then you have something like a fitness function, for example, that gives each individual a fitness, and then you select the n fittest individuals and mutate them somehow, and you go to the next round. All this wasn't here in the evo loops. There was no concept of an individual loop. It was just a pattern of cells. But for us as observers, it looked like an individual loop. But it's not an entity in the program. And it's like ourselves, for example. We consist of atoms. And I don't think there's a program running that chooses the fittest humans and mutates them. No, it's just happening by local interactions of molecules with each other. So this is the closest, I think, the closest to artificial life we really have, because there we don't need this concept of a fitness function or concept of individuals or hard-coded genetic algorithms. It all happens out of the inner dynamics of the system. Yeah, and the evo loop rule I've showed you, it's an existence proof of artificial life in cellular automata, because I've already calculated how many rules there exist for some neighborhoods and some number of states. This is a huge number. And by showing the evo loop, I've shown you one point in this huge space. And I've proven that there is at least one interesting point in this space. So by using evolution or other things I demonstrated, one could explore this space and maybe find much more interesting rules. And that's what the software really is written for. Because I haven't seen such software before. That's why I started it. So that brings me to the end. Yeah, I say it again. There's a huge space of possible cellular automata. I've presented some tools for exploring this space. And I gave some existence proofs that there are some interesting points in this space. And I hope I got you interested in cellular automata again. And if you're interested in the software, you can, of course, get it here, source code included, with all rights on your side. Yeah, that's it. Are there any questions? Yeah? He asked if I've done anything in more than 2 dimensions. The engine, so the classes that are behind this, it supports arbitrary neighborhoods, arbitrary dimensions, and everything like this. But the user interface only supports 2-dimensional stuff. And it would be a problem for visualization. But the classes that are behind it are really abstract. They can do anything. And I've tried it once in 3D, but I didn't have any visualization code. So it was awkward. Yeah, if you Google for 3D and cellular automata, you'll find some things. Yeah. It would be very interesting, really, to do this. Yeah. Anything else? Yeah.
I have a question about the evoloop. You mentioned that it was created on purpose by this researcher. And how many rules does this evoloop consist of?
It's about 500 rules, but with symmetries and all this, it gets more. But about these, and then there are many default rules. So for most of the states, it just dies. This test state develops, so it dissolves everything again. Yeah, 500 rules and some more because there's symmetries and stuff like that. But
and can one say if this is the minimal set of rules? So are there any rules which you don't need also?
It's very hard to prove such things mathematically. I don't know if you can say this, but I can tell you something about the history of the evoloop, because it really goes back to John von Neumann. John von Neumann had this idea. Why did he invent cellular automata? Because he wondered why living things can reproduce without degenerating, or even get better with time. And so he designed this cellular automata with 29 states. And it is really a machine. If you see it, I tried to, there's an open source implementation for the automata John von Neumann created, but it has some weird self-written compressed file scheme, and so I wasn't able for today to extract the rule out of there and load it into my program. Otherwise, I would have shown it to you, but you can find it on the internet. It's really a huge cellular machine that has some cellular tape where it reads states out and constructs another machine according to the information on the tape. Then there's a second machine that can copy tapes. And so you have a tape for the machine that can create another machine out of a tape. And you have a tape for this machine and a tape for the tape copier. And then the tape copier also copies the tapes. And then you get reproduction. Perfect. And interesting, von Neumann didn't see any computer simulations of it. He just showed it mathematically that it works. And today there are simulations, but he died way too early to ever see it. And some small parts of this cellular machine, they are similar to the loop. They are similar to the evoloop. And Christopher Langton, I don't know if he's an artificial life researcher, he just took the rules that are needed for this loop and made a self-replicating structure out of it. But the problem with this loop from Christopher Langton, it was that in the paper he published, he didn't define many possible states. And so nobody knew what to do with them. And usually you just did something, and then eventually the loops just crashed into each other and became dysfunctional. And so then this Japanese guy came along and said, we need some way to clean the space up again. And he added some states and some transitions to do this. And that's where it is now. But I don't know if probably it could be done with lesser states, with different neighborhoods. But it's hard to find an optimal solution to this, or to prove something like this. Yeah?
You can create
any Turing machine, yeah?
Self-reproducing machine. So what for do you need 500 rules if you can do the same with 3 rules?
This goes, first of all, because I think it's interesting in itself, although, and then a Turing machine is not everything, because of course you can create Turing machines with game of life, and I've seen game of life patterns that calculate prime numbers or stuff like this. But if you just start with a random game of life pattern, you won't get anything interesting. And the binary counter we've seen, the decreasing binary counter, it just forms out of random data. I loaded a pattern now because I didn't want to sit here 10 minutes doing random initialization, waiting for an interesting pattern to emerge, but it gets into existence just by itself, just by creating random chunk. And because this is also what we are, I mean, living things. There's no creator that creates initial pattern, I think. And so it has to form out of random stuff. And I'm trying to look for cellular automata that form out of random patterns. Cellular automata?
Who created the rules for the cellular automata which works on the random state?
You mean in the universe or here? I don't know.
It's the same problem delegated to a different level. So.
You're right, yeah. I don't want to discuss this now, but maybe later. Okay. Other questions? No.
Yeah.
Just go. Yeah.
Yeah, just. The evolup rule set was clearly designed by a scientist, but the rule set for your binary counter, did you design it or did it occur just by mutation?
It was by mutation. I can show you some precessors because I saved the rules along when I designed the rules, so I could show it to you. So this was the original Gardener, as I called it then. Yeah, and it looked like this. I don't know how I got to this, but I just started with some initial rules and mutated along. So this was this rule. It looked interesting, and then I made this by mutation. But here now everything died out. So I made it more active by adding random rules, basically. And then it got the ones I showed you. This was the rule that produces the binary counters. As you can see here, now here there are binary counters, totally out of random data. For example, here's a mutation of this again. Okay, so this was really created with mutation, not designed in any way. Okay. There was another question? Or?